Hello everyone, so we're going to do another video. We're going to do a problem here. This is an example of how to find the natural frequency of a system. So we've got a bar, actually, there's a wall here, basically, or a fence or something like that. It's got a door, and this door here is, so let's say this is just a fence. So this is the top view, basically, top view of the system, and there's a spring connected to the door. The door, it basically is, this is the top view of the door. It's not a door, but it basically a rod that basically rotates accordingly with the spring. So it's free to rotate in the horizontal plane, right? And then now we've got, and then the K value is given. The K value is 2,000 newtons per meter. Okay, so we're asked to find the natural frequency of this system. So first of all, let's we're going to have to find the, so remember we talked about this before, and we said that for rotational systems we're going to take the sum of moments, and that's exactly what we're going to do here. The sum of moments, which is going to equal to JO, that's the polar inertia of the system, polar inertia of the system, or mass moment, and we've got the angular acceleration. So let's do the free body diagram of this figure here. So this is your axis of rotation, that's your bar or rod, and it's got the force of the spring, that's your Fs, and we're going to do a y-axis here and an x-axis basically. And this is the direction of rotation. When taking sum of moments, we consider direction of rotation to be positive, to be the positive moment, basically. Positive moments. So when taking, this is going to be the positive moment. It's your FBD, free body diagram, and we forgot to mention that the length of the rod is basically L. That's your L. So hence, this makes it L over 2, the length from here to here. So, oh, there's no need for that line to be there. Okay, so let's do the sum of moments. That's for the equation of motion, right? Equation of motion. And we're going to do a sum of moments. About point O, the axis of rotation. So you do the, that's point number 1, and point number 2, sum of moments about axis of rotation. Now we've got, so basically what we have here is, that's going to be equal to j times your angular frequency, angular acceleration. Okay, let's do that. So obviously the force is acting in, is going counterclockwise, so it's going to be a negative Fs times the distance, the horizontal distance, perpendicular distance. So this distance here, we're going to call that x, is equal to cosine theta L over 2. So that's the distance. That's basic trigonometry. You can go back and review trigonometry if you get stuck on that, or I can just do that for you right here. So that's your theta, and that's your L over 2. We want to find this distance here. That's going to be cos theta equals to x, which is our adjacent, over the hypotenuse, which is L over 2. So that's how you get x is equal to L over 2 cosine theta. We've got that. And now for doing all these equation of motions, so that's point number 3, we have to set a rule. So cosine theta, we're going to use approximation because all these systems here, we're going to assume, let's do that. We're going to assume small angles. So cosine theta is basically a 1, sine theta is basically a theta. That's your approximation there. So that's going to be, that's going to be an L over 2. So L over 2, and that's about it pretty much. So then rearrange, so j in theta double dot dot plus, bring it to the other side, and then Fs L over 2 equal to 0. Now what's Fs? So let's go to the second page. It's got Fs is basically your k times your displacement. So if we go back and see how much did the system displace, it displaced by this. So we're going to consider the rod. Let's draw this here, right here. So in equilibrium, the rod is basically like this, and it moved, translated, or rotated by this much. So it moved from point A to point A naught. A naught. Oh dear. So A naught. So let's do that. So that's our theta. So then we're going to use sine law. So sine theta is equal to, that's our distance, y. So y over L over 2, that's your L over 2 right there. So then y is basically L over 2 sine theta. And a small angle approximation, that's all over L over 2 times sine theta. So we go back here and we're going to take this, basically. We're going to take this equation, copy it, and go back. Let's go to a new, clean, fresh page. We're going to paste that there. Sweet. So let's sub in the S. That's going to be K times L over 2 theta, bracket close, and times L over 2 equals 0. So that's going to be a K over 4 L squared theta. So doesn't that look similar to the equation of motion right there? So what we're going to do is basically divide through this entire thing, divide by j all the way through the entire equation, basically. What we get is theta double dot plus k over 4 L squared theta by j, sorry, theta equals 0. So that's what we want. That's what we're looking for. Use another color. That's your, let's take that whole thing, copy, take it to another page, paste it here. That's what we want. This is our natural frequency. K over 4 L squared over j. So we can simplify this more if we know what j is. So for a simple rod, you can j rotating about its axis is 1 over 12 times mass times L squared. So let's plug in that back in there, and we'll get K over 4 L squared 1 over 12 m L squared. So the L squared will cancel, and then you'll basically get this 12k over 4m. That's your natural frequency. So you found your natural frequency, and that's pretty much what we were asked for. And just a quick note there, and then you can sub in your values, whatever the mass is and whatever your k value is. But it's really important to basically know how to figure out the equation of motion, which is your primary thing. And the next thing is basically figure out, recognize that the natural frequency of the system from the equation of motion. And that's about it. Thank you very much.